Hello everyone, welcome back to my channel. Today, we will explore a very exciting question. Can artificial intelligence help us see underground? Deep below the Earth's surface, fluids are moving through rocks, pores, and fractures. These fluids may be CO2 for carbon storage, hydrogen for future clean energy storage, hot water for geothermal energy, or groundwater in environmental systems. But there is one major challenge. We cannot directly see what is happening underground. We only have limited measurements from wells, seismic surveys, and monitoring tools. So, how can we understand hidden underground flow? How can we know where the plume is moving? How can we know where pressure is increasing? And how can we make safer decisions? This is where the idea of an AI digital twin becomes powerful. By combining physics simulation, Python-based dynamic demos, and deep learning, we can create a virtual system that helps reveal what is hidden underground. AI does not physically open the Earth, but can help us transform hidden subsurface behavior into visible prediction maps. Underground flow is important because it connects many of the world's most important energy and environmental challenges. For CO2 storage, we need to make sure that injected CO2 stays safely underground for a very long time. For hydrogen storage, we need to understand how hydrogen moves, how much can be recovered, and whether the storage system remains safe during repeated injection and withdrawal cycles. For geothermal energy, we need to track how heat and fluids move underground, because this controls energy production and long-term performance. For groundwater protection, we need to understand whether any injected or naturally occurring fluid could affect freshwater resources. Although these applications look different, they share one hidden process: subsurface fluid flow. That is why understanding underground flow is not only a scientific problem. It is also a climate, energy, and safety problem. If we understand subsurface flow better, we can design safer and smarter energy systems. This slide shows the core challenge. The underground is invisible. In real projects, we may have only a few wells. These wells give us important information, but only at very limited locations. Between the wells, the fluid plume can move through complex rock layers, and we may not observe the full pathway directly. The Python demo result on this slide shows a hidden plume moving underground. The colorful region represents the fluid plume. The monitoring points show how limited our measurements can be. This is similar to trying to understand a whole movie by seeing only a few snapshots. We may know something, but we do not know everything. That is why prediction becomes so important. We need a tool that can combine limited observations, physics knowledge, and simulation data to estimate what is happening between measurement points. In subsurface engineering, we often make important decisions with incomplete information. Physics-based simulation is one of the most important tools in subsurface engineering. A reservoir simulator can solve the governing equations for fluid flow, pressure propagation, and saturation changes. It can help us understand how injected CO2, hydrogen, or water moves through the reservoir. In the Python demo result, we see a simplified reservoir simulation. The injection well introduces fluid into the system. The plume grows, and pressure also propagates through the domain. This type of simulation is powerful because it is based on physics. It can capture important processes such as flow direction, pressure buildup, and saturation evolution. But there is also a limitation. Detailed simulations can be computationally expensive. If we need to test thousands of geological scenarios, different injection rates, uncertainty cases, and long-term forecasts, the cost can become very high. Physics simulation is reliable, but it is not always fast enough for real-time decision-making or large uncertainty analysis. Now we introduce the AI digital twin. A digital twin is a virtual copy of a real system. In this case, it is a virtual representation of the underground reservoir. The workflow is simple. First, we generate simulation outputs from physics-based model. These outputs may include pressure, saturation, plume shape, or other subsurface variables. Then, the AI model learns patterns from many simulations. It learns how the plume evolves, how pressure spreads, and how geological structure affects fluid movement. After training, the AI model can make predictions much faster than running a full simulator again and again. This is very important. AI is not replacing physics. Instead, AI is learning from physics-based simulations and helping us accelerate prediction. The best AI digital twin is not a black box. It is a fast prediction tool guided by physical understanding. This is the first Python demo result, plume migration. The plume starts near the injection zone. As time passes, it moves through the reservoir and follows easier pathways in the rock. Notice that the plume does not move as a perfect circle. It stretches, bends, and changes shape. This happens because the underground is heterogeneous. Some pathways allow fluid to move more easily, while other regions slow it down. The time sequence at the bottom shows how the plume changes step by step. At early time, the plume is small. Later, it becomes longer and more complex. This simple demo helps us understand a very important idea. Underground flow is dynamic. For CO2 storage, this plume may represent injected CO2. For hydrogen storage, it may represent hydrogen gas. For geothermal systems, a similar map may represent heat or fluid movement. The second Python demo result shows pressure buildup. When we inject fluid underground, pressure increases near the injection well. Then, this pressure spreads outward through the reservoir. An important point is that pressure can spread faster than the visible plume. This means that risk may develop even in regions where the injected fluid has not yet arrived. For example, high pressure may affect caprock integrity, faults, fractures, or nearby wells. In CO2 storage, pressure management is essential for long-term safety. In hydrogen storage, pressure control is also important during injection and withdrawal cycles. The pressure map on this slide shows where pressure is highest and how it expands over time. The red and orange colors indicate high-pressure regions, while blue indicates lower pressure. This slide shows one of the most visually important ideas, from blurry to sharp. On the left, we have a coarse input. This is similar to a low-resolution simulation or limited observation. It shows the general plume location, but important details are missing. On the right, we have an AI-enhanced result. The plume boundary is sharper. The internal flow structure is clearer. The model gives us a better view of the hidden subsurface behavior. This is similar to improving a blurry medical image. The goal is not only to make the image look beautiful. The goal is to recover useful information that supports better decisions. In subsurface applications, sharper plume fronts can help us understand where the fluid is moving, where monitoring should be focused, and where risk may appear. The fourth demo result focuses on forecasting. A useful AI digital twin should not only describe the current state. It should also help predict what may happen next. In this slide, we start from the current plume state. Then the AI model forecasts the plume evolution at future time steps. This is important because subsurface decisions are forward-looking. We need to know where the plume may move next week, next month, next year, or even decades into the future. For CO2 storage, forecasting helps us plan monitoring and verify storage safety. For hydrogen storage, it helps estimate gas movement and recovery. For geothermal energy, it helps predict heat front movement and long-term production behavior. Prediction alone is not enough. We also need uncertainty. No model is perfect. A responsible AI digital twin should tell us not only what it predicts, but also where it is unsure. On the left, we see the predicted plume map. On the right, we see the uncertainty map. The uncertainty map highlights regions where the model has lower confidence. These regions may appear near fast-moving fronts, complex plume boundaries, strong heterogeneity, or areas with limited training data. This is extremely useful. Instead of hiding uncertainty, we use it as guidance. If uncertainty is high in one region, we may place more monitoring sensors there, collect more data, or run additional simulations. Now we move from prediction to action. The real value of an AI digital twin is not only producing colorful maps. The real value is helping scientists and engineers make better decisions. From the plume map, we can estimate where the injected fluid is moving. From the pressure map, we can identify pressure risk hotspots. From the uncertainty map, we can decide where more monitoring is needed. This can help answer practical questions. Where should we place monitoring wells? Where should we collect more data? Should we reduce injection rate? Which region has higher risk? Which operation strategy is safer? This is the bridge between artificial intelligence and real subsurface engineering. Let us summarize the main message. The underground is complex, hidden, and uncertain. We cannot directly observe every part of the reservoir. But by combining physics simulation, Python-based dynamic modeling, and artificial intelligence, we can build digital twins that help make the invisible more visible. AI can help us predict plume migration, understand pressure buildup, improve course simulation results, forecast future behavior, and identify uncertainty hotspots. This idea can support many important applications: CO2 geological storage, underground hydrogen storage, geothermal energy, groundwater protection, and environmental monitoring. But the most important message is this: AI should not replace physical understanding. AI should work together with physics to support safer, faster, and smarter decisions. Thank you very much for watching. Please subscribe to the channel for more videos about AI, geoscience, carbon storage, hydrogen storage, geothermal energy, and sustainable subsurface engineering.